Bismillahirrahmanirrahim. We are done with chapter number 2 of the fiber optic communications. We are going to start chapter number 3 today. We have got the applications of Maxwell equations in chapter number 3. So we need to review all the 4 equations of Maxwell in instantaneous as well as phasor form. So before making discussion on all the 4 equations of Maxwell, let us consider the instantaneous values of different electrical quantities and the phasor values of different electrical quantities. We consider table number 1. In table number 1, we consider the instantaneous values on the left hand side and the phasor values of these electrical quantities on the right hand side. So here is the instantaneous value of the electric field intensity, and we know that force per unit charge is known as electric field intensity. The unit of the electric field intensity is volt per meter. Here is the phasor value of the electric field intensity. If you guys study the standard books, this is how the phasor value of an electrical quantity is represented in the standard book. But I have taken these materials from my personal book, and in my personal book, this is how I represent the phasor value of the electric field intensity. So anyhow, different symbols are used for the representation of the phasor quantities in different books. I will use this particular notation. So we know how to represent the instantaneous value of the electric field intensity and the phasor value of the electric field intensity. This is the instantaneous value of the electric flux density. And what is electric flux density? Electric flux density is the charge per unit area or the flux per unit area. So the flux per unit area is known as electric flux density. The unit of the electric flux density is coulomb per square meter. So here is the instantaneous value of the electric flux density, and here is the phasor value of the electric flux density. So this is how we represent the instantaneous value of the magnetic field intensity. And this is how we represent the phasor value of the magnetic field intensity. The unit of the magnetic field intensity is ampere per meter. Right? Now, we define magnetic flux density. We know that the magnetic flux per unit area is known as magnetic flux density. The unit of the magnetic flux density is Weber per square meter or Tesla. And this is how we represent the phasor value of the magnetic flux density. Here is the symbol for the conduction current density, the current per unit area. and the unit of the conduction current density is ampere per square meter. So this is the instantaneous value of the conduction current density, and here is the phasor value of the conduction current density. So if we consider this table, these are the instantaneous values of different electrical quantities, and these are the phasor values of different electrical quantities. So we are going to consider the 4 equations of Maxwell's in instantaneous as well as phasor form. So we consider the first equation of Maxwell. Here is the first equation of Maxwell. This is the first equation of Maxwell. That is, the divergence of the electric flux density is equal to rho v. And what is rho v? Rho v is known as volume charge density. And the charge per unit volume is known as volume charge density. So rho v is the volume charge density, that is the charge per unit volume. So equation number 1 gives you the instantaneous form of the first equation of Maxwell. We want to convert this equation into phasor form. And if you guys want to convert any the instantaneous form of any equation into phasor form, there are 2 steps. You guys can do it in 2 steps. Step number 1, you guys have to replace the instantaneous value of the this is how we represent the instantaneous value. So we need to replace the instantaneous value of the electric flux density by the phasor value of the electric flux density. So here is step number 1. In step number 1, we need to represent we need to replace the instantaneous value of the electrical quantity by the phasor value. Step number 2. In step number 2, we need to replace curly by curly t by j omega. So if we have curly by curly t, we need to replace this curly by curly t by j omega. Okay, so this is the instantaneous form of equation number 1, and we want to convert it into phasor form. In order to convert the instantaneous form of equation number 1 into phasor form, we replace the instantaneous value of the electric flux density by the phasor value, and that's it. So the divergence of the phasor value of the electric flux density is equal to rho v, and this is the phasor value or the phasor form of the first equation of Maxwell. So let us consider the second equation of Maxwell. So here is the second equation of Maxwell, which says that the divergence of the magnetic flux density is equal to 0. So this is the second equation, that the divergence of the magnetic flux density is 0, and we want to convert this equation into phasor form. In order to convert this equation into phasor form, we replace the instantaneous value of the magnetic flux density by the phasor value of the magnetic flux density, and that's it. So the divergence of the magnetic flux density will be equal to 0, and this is the second equation of Maxwell in phasor form. we want to go ahead and we are going to consider the third equation of Maxwell in instantaneous form. So here is the third equation of Maxwell in instantaneous form of representation. The curl of the magnetic field intensity is equal to J. We know that J represents the conduction current density plus curly D by curly T, and curly D by curly T is known as displacement current density. So we want to convert the instantaneous form of this equation into phasor form. So in order to convert the instantaneous form of this equation into phasor form, we replace the instantaneous value of H by the phasor value of H, the instantaneous value of J by the phasor value of J, the instantaneous value of D by the phasor value of D, and we replace curly by curly T by J omega. So equation number 3 in phasor form. So this is how we represent the third equation of Maxwell in phasor form of representation. The curl of the magnetic field intensity is equal to the conduction current density J plus J omega D. Now we are going to consider the last equation of Maxwell in instantaneous as well as phasor form of representation. So this is the fourth equation of Maxwell in instantaneous form. And in this equation, the curl of the electric field intensity is equal to minus curly B by curly T. This equation states that a time varying magnetic field can create a time varying electric field, and equation number 4 is in instantaneous form. So what we do, we want to convert the instantaneous form of this equation number 4 into phasor form. So in order to replace the instantaneous form of equation number 4 into phasor form, we replace the instantaneous value of the electric field intensity by the phasor value. Similarly, the instantaneous value of the magnetic flux density by its phasor value, and we replace curly by curly T by J omega. Right? So we consider the last equation of Maxwell in phasor form. So this is how we represent the fourth equation in phasor form of representation. The curl of the electric field intensity will be equal to minus J omega B. So we are done with all the four equations of Maxwell's in instantaneous as well as phasor form of representation. So we go to study the propagation of the electromagnetic wave in a lossless dielectric medium. So light is an electromagnetic wave. We know that light is electromagnetic wave. So basically, in this particular topic, we study the propagation of the light wave in a lossless dielectric medium. What is a lossless dielectric medium? Lossless dielectric medium is an ideal medium, and the attenuation of the wave does not take place in this particular medium. The conductivity of this medium is always equal to 0. So lossless medium is an ideal medium. This medium does not exist in practice, and the attenuation of the signal does not take place in this medium. The signal does not attenuate in the lossless medium. The loss of the signal will not take place in this particular medium. Mathematically, the conductivity, which is represented by sigma, is always equal to 0 in this particular medium. What is transverse electromagnetic wave. So let us talk about transverse electromagnetic wave. In the transverse electromagnetic wave, the electric field intensity and the magnetic field intensity and the velocity of the wave are normal to each other. So let us consider this diagram in the next slide. This diagram will let you know that these three electrical quantities are normal to one another. So we consider the electric field intensity, magnetic field intensity, and the velocity of the wave in this particular figure. You see, the electric field intensity of the wave is along x-axis, and the unit vector along x-axis is represented by ax. Similarly, the magnetic field intensity of the transverse electromagnetic wave is along y-axis, and the unit vector along y-axis is represented by ay, and the velocity of the wave is along z-axis, and the unit vector along z-axis is represented by az. So the electric field intensity of the transverse electromagnetic wave is normal to the magnetic field intensity, and these two fields are normal to the direction of the propagation of the wave, the direction of the motion of the wave, the direction of the speed of the wave, the direction of the velocity of the wave. So in this particular diagram, this transverse electromagnetic wave is propagating along z-axis in the z direction, right? So the magnetic field intensity is equal to, the magnetic field intensity is normal to the electric field intensity, and the direction of the speed of the wave is normal to both the fields, that is electric field intensity as well as magnetic field intensity. Okay, so we are going to derive the equation for the electric field intensity of the transverse electromagnetic wave in a lossless medium. I have mentioned earlier that lossless medium is an ideal medium. The loss of the signal does not take place in this medium. Mathematically, the conductivity of the medium is zero. So we consider the first equation over here, which is the Maxwell equation. So we consider this equation of Maxwell. There is the curl of the phasor value of the electric field intensity is equal to minus j omega multiplied by the phasor value of the magnetic flux density. So we know that the magnetic flux density is equal to mu, which is the permeability of the medium, multiplied by the magnetic field intensity. So we put the value of the magnetic flux density in this particular equation, and we get this particular equation. So putting the value of the magnetic flux density in the first equation, we get the curl of the phasor value of the electric field intensity, which is equal to minus j omega mu multiplied by the phasor value of the magnetic field intensity. So what we do, we take the curl of the quantity on the left hand side of this equation and the curl of the vector quantity on the right hand side of this equation. So if we take the curl of the left hand side of equation number 8.28, we get equation number 8.29. So we take the curl of the quantity on the left hand side of the previous equation. So the curl of the electric field intensity will be equal to minus j omega mu multiplied by the curl of the magnetic field intensity. So we take the curl of a vector quantity always, right? So what we do, we will put the equation of del cross H in equation number 8.29. We recall another equation of Maxwell. This is another equation of Maxwell, and this equation is in phasor form. This equation of Maxwell says that the curl of the magnetic field intensity is equal to J plus J omega T. And what we do, we put this value in equation number 8.29. So if we put this value in equation number 8.29, we get equation number 8.31. So the curl of the electric field intensity is equal to minus J omega mu, and this is the value of del cross H. So del cross H is equal to J plus J omega D. So we obtain equation number 8.31. Now we know that the electric flux density is equal to permittivity multiplied by the electric field intensity. We know this relationship between the magnetic the electric flux density and the electric field intensity. So what we do, we put the value of D in equation number 8.31. If we put the value of D in equation number 8.31, then we get equation number 8.32. The curl of the electric field intensity will be equal to minus J omega mu into J plus J omega epsilon E. So we replace the electric flux density by epsilon E, right? And we know that the conduction current density will be equal to the conductivity, which is represented by sigma, multiplied by the electric field intensity. So what we do, we put this value of J in equation number 8.32. So if we put this value of J in equation number 8.32, we get equation number 8.33. That is the curl of the electric field intensity will be equal to minus J omega mu into sigma E plus J omega epsilon multiplied by the electric field intensity. As this medium is an ideal medium, this medium is lossless medium, so the conductivity of this medium is 0. So we put the conductivity we put the value of the conductivity in equation number 8.33. So if we put the value of the conductivity in equation number 8.33, you see the conductivity of this medium, you see the conductivity of the ideal medium is 0. So if you put this value in equation number 8.33, we get, you see, this term in equation number 8.33 will be 0, and we simplify the remaining term, and we know that J square is basically equal to minus 1. Okay, so we will replace J square by minus 1 in equation number 8.33. So let us go to this particular slide, and what we do, we put the value of sigma in equation number 8.33, and we simplify the right hand side of equation number 8.33. So the curl of the electric field intensity will be equal to minus omega square mu epsilon E. Alright, so this is equation number 8.34. Now we can show that the curl of the electric field intensity is equal to minus del square multiplied by the phasor value of the electric field intensity, and del square E is basically equal to curly square by curly x square of the electric field intensity plus curly square by curly y square of the electric field intensity plus curly square by curly z square of the electric field intensity. So del square E is basically equal to the right hand side of this particular equation. So what we do, we replace this left hand side by minus del square multiplied by the phasor value of the electric field intensity. Okay, and if we do it, so equation number 8.3 can be written as minus del square E will be equal to minus omega square mu epsilon multiplied by the phasor value of the electric field intensity, and we rearrange this particular equation. Okay, so if we rearrange this equation, what do we have here? J square. Okay, there is a mistake over here. Let me rectify this mistake. Okay, so what do we have? Basically, you guys need to replace this minus sign by plus sign over here, and this minus sign by plus sign over here. Okay, so the minus sign on the right hand side should be replaced by the plus sign. Okay, so if we rearrange equation number 8.345, we get equation number 8.36, right? And this equation is known as the wave equation, right? So this is the wave equation in a lossless medium. Okay, we know that the wave is moving along z-axis, okay, where z represents the distance traveled by the wave. So as the wave is moving along z-axis, this is why the electric field intensity will be changing with respect to z only. So the electric field intensity will be equal to the function of z. And if the electric field intensity is the function of z, then what we do, we consider this particular equation, right? So if the electric field intensity changes with respect to z only, the first term on the right hand side of this equation will be 0. The second term on the right hand side of this equation will be 0, and we will be left with the third term only, because the electric field intensity is changing with respect to z only. Alright, so let us go to this particular slide. You see what we do, we replace del square E by curly square E by curly z square. Why? Because the electric field intensity is changing with respect to z only. It's not changing with respect to x, and it's not changing with respect to y as well. So if we replace del square E in equation number 8, if we replace del square E in equation number 8.36 by curly square E by curly z square, so we obtain equation number 8.37. You see, equation number 8.37 says that curly square by curly z square of the electric field intensity will be equal to omega square mu epsilon multiplied by the phasor value of the electric field intensity, which is equal to 0. This is second order homogeneous differential equation. You see, this equation is known as second order homogeneous differential equation. We need to find out the solution of this second order homogeneous differential equation. If you want to find out the solution of the second order homogeneous differential equation, we need to find out the characteristic equation or the auxiliary equation of equation number 8.37. So equation number 8.37 is the second order homogeneous differential equation. We want to find out the solution of equation number 8.37. In order to find out the solution of equation number 8.37, we need to find out the characteristics or the auxiliary equation of equation number 8.37. So this is our objective now. What is our objective? We need to find out the auxiliary or the characteristic equation of this second order homogeneous differential equation. So if we want to find out the auxiliary equation of the second order homogeneous differential equation, we need to replace curly by curly z by m. So let us replace this curly by curly z in equation number 8.37 by m. So we replace this curly by curly z in equation number 8.37 by m. So we get equation number 8.38. So equation number 8.37 can be written as, we have m square e plus omega square mu epsilon e, which is equal to 0. So the electric field intensity on the left hand side of this equation is a common quantity, right? So the same equation can be written as m square plus omega square mu epsilon multiplied by the phasor value of the electric field intensity will be equal to 0. If we focus on equation number 8.39, the product of two terms is 0. So either the first term or the second term will be equal to 0. The electric field intensity of the wave is not equal to 0. Why? Because it represents the existence of the wave in the lossless medium. If the electric field intensity of the wave is 0, it means that the wave does not exist in this medium at all. So you guys cannot replace the electric field intensity by 0. So what we do, we replace the first term by 0. If we replace the first term by 0, we have m square plus omega square mu epsilon, which is equal to 0. This is a very important equation, and this equation is known as the auxiliary equation of the second order differential equation. So this is the auxiliary equation of the second order homogeneous differential equation. Okay, so we have found the auxiliary equation of the second order homogeneous differential equation. In order to find out the solution of this second order homogeneous differential equation, we need to find out the roots of this auxiliary equation, right? So let us find out the roots of this auxiliary equation. So we find out the roots of the auxiliary equation. These are the roots of the auxiliary equation, and you see the roots of the auxiliary equation are imaginary. All right, so you see I have beta over here, which is known as the phase constant. I replace this quantity by beta in my book, but if you consider the book of the fiber optic communication system, so they represent this quantity by k, which is known as propagation constant. So there are two roots of the auxiliary equation, right? So what do we have? We have jk plus minus jk, which will be equal to plus minus j omega under root mu epsilon. This is epsilon, okay? This quantity is epsilon, right? Let me make a correction over here. This quantity is epsilon, okay? So we will represent, as the roots are imaginary, so we will replace m by plus minus jk, and don't consider beta, replace beta by k, and k will be equal to plus minus j omega. So k, you guys need to consider k over here instead of beta, will be equal to omega under root mu epsilon. So this is the propagation constant, and this is how we calculate this propagation constant. So please replace beta in this particular case by k, because if you study the book of fiber optic communication system, they use this particular symbol instead of beta. Okay, so there are two roots of the auxiliary equation. The roots are imaginary. One root is positive and the other root is negative, right? So we want to discuss the solution of the second order differential equation. Once again, please replace this beta by k. Okay, please replace this beta by k, which is known as propagation constant. So there are two roots. One root is m1, which is equal to jk, and the other root is m2, which is equal to minus jk, right? So these are the two roots. Instead of beta, you guys need to consider the propagation constant, that is k. So what we do, we find out the solution of the second order homogeneous differential equation. So the solution of the second order homogeneous differential equation will be in this format. So the phasor value of the electric field intensity will be equal to E naught into e raised to power minus j beta z. Please replace this beta by k, so you will have e raised to power minus jkz plus eb into e raised to power j beta z. What is ax? Ax is a unit vector along x-axis. Electric field intensity is a vector quantity, and if you consider the previous diagram, this vector quantity was along x-axis. So the solution of the second order homogeneous differential equation will be in this form. You see, there are two components of the electric field intensity. This is one component, and here is the second component. So the first component represents the component of the wave which travels along positive z-axis, and this component is known as forward traveling wave, FTW. This wave is known as forward traveling wave. The component which moves along positive z-axis is known as forward traveling wave. Okay, I am talking about this component. Now the second component, I am talking about this component, represent the component which moves along negative z-axis, right? So what we do, we are going to consider the figure of this particular topic once again. You see, in this particular figure, the electric field intensity is moving along positive z-axis only, right? There is no component of the wave which is moving in the negative z-axis. You see, the wave is moving along positive z-axis only. No component of the wave is moving along negative z-axis. So as no component of our wave is moving along negative z-axis, we need to eliminate this component. We need to ignore this component. We need to delete this component from the solution of the second order homogeneous differential equation. So let us consider the solution once again, and as no component of our wave is moving along negative z-axis, so we need to delete this component, we need to ignore this component. As the wave is moving along positive z-axis, so we will have to consider the first component of equation number 8.42 only. So the solution of the second order homogeneous differential equation will be in this form, and this is the phasor value of the electric field intensity, right? So please replace this beta by k. It's very important for you guys, because the book of fiber optic communications is not using this beta symbol. That book is using k. So this is the phasor value of the electric field intensity of the light wave in a lossless medium. So the phasor value of the electric field intensity of the light wave in a lossless dielectric medium will be equal to E naught into e raised to power minus jk, replace beta by k, minus jkz multiplied by ax. Ax is a unit vector along x-axis, which gives you the direction of the electric field intensity in this particular equation. So here is the instantaneous value of the this is the phasor value, not instantaneous. I'm sorry. This is the this is the phasor value of the electric field intensity of the uniform plane wave. The transverse electromagnetic wave is also known as uniform plane wave. And we can write down the same equation in instantaneous form. So in instantaneous form, the electric field intensity will be equal to E naught, where E naught is the amplitude of this field, into sine of omega t minus kz. So please, you guys will have to replace this beta by k. This is a very humble request, right? So the instantaneous value of the electric field intensity will be equal to E naught into sine of omega t minus kz multiplied by ax. This is the instantaneous value of the electric field intensity of the uniform plane wave in a lossless dielectric medium. In the next topic, we will study the propagation of the uniform plane wave in a lossy medium. Thank you so much.